Welcome to Unit 7, Lesson 3, Transformations of Sine and Cosine Functions. Now that we understand what A, B, C, and D do, we are going to use this lesson to combine all those transformations and translations and look at and evaluate how does that affect the graph of y equals sine x and y equals cosine x. So the first example here, we have y equals negative 2 cos theta plus pi minus 1. So we have a vertical stretch of negative 2, horizontal shift of pi, and a vertical shift of minus 1. So you can see there's an explanation on the right there for each of the transformations that this graph has gone through. It's undergone a reflection over the x-axis, or the theta axis in this circumstance, and then a vertical stretch by a factor of 2. So it's flipped and then stretched vertically by a factor of 2. Don't forget from the previous unit, and there's a note up here, don't forget that the stretches and reflections, A and if there was a B, happen first before the graph moves. So stretch it and flip it before you move it left, right, up, or down. Now, just like in the previous units, we have those mapping points. So once you know the coordinates and how they're going to be affected by the transformations, you can just write out the mapping points, and then this problem becomes very easy. You can just pick a few points that you know the graph would hit. 0, pi, and 2 pi are always really good ones. And from there, you can just map out the points. You don't necessarily have to write out the points, but you can use them as your guide to creating your graph. Below that, we have an additional example. Draw one cycle of y equals 3 sine 2x minus 2 pi over 3 plus 2. I just wanted to remind you of something, which is that within these brackets, because there's a coefficient in front of the x here, but it's not isolated out, remember that you have to divide out that term so that you get an isolated b value. If you're looking at the graph going, why the heck is it pi over 3 shift when it's 2 pi over 3 here? And the reason being is that when we divide out that 2, all we're left with in that c term is negative pi over 3, which is a horizontal shift to the right. So we're going to take the original sine graph, multiply it by 3 for the y values. And for the x values, we're going to divide them by 2. Remember, for the b value, if you're multiplying by a whole number here, you divide the x values by it. And if there's a fraction here, you multiply by the bottom of the fraction. But in this case, we have a whole number, so divide by 2. So our mapping points become x divided by 2 plus 2 pi over 3. And our y coordinates are 3 times y plus 2. Once you've done that, you can just plug in your coordinates. A good one to start with, which we did here, is 0, 0. Okay, and just go from there. Now, the domain and range of this function, they've changed a little bit. The domain is, of course, still negative to positive infinity, but the range is negative 1 to positive 5. On the back of this sheet, we have just 2 more examples. It asks you to draw 2 cycles of the following. So we have the cosine pi over 30, t minus 15. Remember, this just represents y, and this spot is x. So our points, they will go to x times 30 over pi plus 15. Okay, that from B and C there. And then our y coordinates stay exactly the same because there's no value of A or D. So you can just pause the video and copy down this example. Further down the page, we have the sine function, 12 sine times pi over 3, x minus 2 minus 14. So our mapping points become 3x divided by pi plus 2 and 12y minus 14. So again, you can just plug in the mapping points and go from there. The next thing that you need to be able to do is determine an equation from a graph. So we have this original graph. The graph shows the function y equals f of x. So step 1, write the equation of the function in the form y equals a sine b x minus c plus d, where a is greater than 0. Step number 1, locate the axis or midline. It determines the value of d. So if we just look at this graph of the sine function, it goes from 0 to 4. Halfway through is at 2. So that becomes our d value. It is 2. Then we need to solve for a. These are the two easy ones that you can see just from looking at the graph. So to solve for a, you just take the maximum, subtract the minimum, divide by 2, and in this situation, a is also 2. Okay, so a and d are already taken care of, super simple and straightforward. The next part, you need to determine the period and the value of b. So there's two different ways you can do this part of the problem. Just do whichever one suits you and whichever one's easiest for you and go from there. In method 1, what you're going to do is just count the number of cycles in 2 pi. So you're going to determine the number of cycles in a distance of 2 pi. So 2 pi is here. In this function, we have 1, 2, 3 cycles. Therefore, the value of b is 3. And the period is 2 over 3. You can see that it repeats beginning right there. In method 2, this is where you do it mathematically. So what you want to do is locate the start and end of one cycle of the sine curve. So the start and of the first cycle of the sine curve that is closest to the y-axis is at x equals pi over 6. Here. And the end is at 5 pi over 6. So here's our start, and here's our end. 1. Okay? So the period then becomes 5 pi over 6 minus pi over 6, which is 4 pi over 6, or 2 pi over 3. Now that we have the period, we're able to solve for the equation of b. We have this formula from previous lessons. Its period is equal to 2 pi over the absolute value of b. So we have 2 pi over 3, we know the period, and then we can solve for the b value. So plug the period in there, equals 2 pi over b, and of course these are equivalent fractions, so b will also be 3. So whichever way you do it is perfectly fine. They both will give you the exact same answer. Just select the one that's the easiest for you. Now our last step that we need to do is determine the phase shift c, so how far left or right has the graph moved from the origin 0, 0, because it's a sine graph. So locate the start of the first cycle of the sine curve to the right of the y-axis. Therefore, c equals pi over 6. I'm just going to go back to the other page to show you what I'm talking about, so you can see the graph. Our sine function typically starts here at 0, 0, and then it oscillates up and down about the x-axis. So you need to look for the starting point that would be at 0, 0. Don't forget that this graph has been moved up and stretched and all that. So find that point, whichever x-coordinate it lies at. This is pi over 6. Whichever x-coordinate lies at, that's your value of c. It's really that simple and straightforward. You just need to look at the graph and find the value of where the graph does start compared to where it should start. Now that we have the values of a, b, c, and d, you just plug it into your formula and fill in your blanks. So 2 sine 3 times x minus pi over 6 plus 2 is our formula that represents that function. Now, from the same graph, we can also produce a cosine graph. And this is an example of that. So don't forget that the cosine graph typically starts here, here at 0, 1. And we've done some stretches and shifts to it. Now, notice that A and D have not changed. B may change. You just need to look at how many times the cosine function repeats in that domain of 0 to 2 pi. but in this circumstance, it stays at 3 curves per 2 pi. The only thing that's changed is that that c shift. It's no longer here, which is the start of the sine function, but don't forget that the cosine function starts as a peak. So the peak, which originally would have been at 0, 1, is now at pi over 3, 4. So you're just having a change in that c phase shift to the right. The last type of question you can be given is you're provided with a graph, you're asked to provide the equation for it, and then answer some questions about the graph. So in this question, we have our midline here at 12. Just draw that in there. That cuts our graph right in half. Now, because we know that, we can see our amplitude or our value of A, the height of the half of the graph. It goes from here 12 to 20 or 12 down to 4. So that A value up and down is 8. Okay. Our D, that's our vertical shift. Wherever that midline falls, that's where your vertical shift is. So here's our D value, plus 12. There's no C. And you might be thinking, well, how the heck do I know that? And you need to understand and remember the shape of the cosine graph. Remember, it starts like this. Of course, this is a depth versus time graph, so there's not going to be any negative y values. But if we had the original y equals cos of x function, you would have a point here, 0, 1. And then it would oscillate back and forth across this x-axis. So you want to look at, does the graph start on the y-axis and is it at a peak? If it is, that tells you that there's no c. So because this graph is starting at the very highest point at time 0, then you can be confident that there is no horizontal shift. So there's no c value. The last thing that we need to do is solve for b. So we know that one period of the graph, one cycle of the cosine graph goes from here, 0, up to 12, and then it starts repeating itself. So the period is 12, and we can solve for b once we know that. So 2 pi over b equals 12. Multiply both sides by b to get the b onto the other side. 2 pi equals 12b, and then divide both sides by 12 to isolate b and get it by itself, and that reduces down to pi over 6 for b. So from here we're able to determine the formula as m, the depth in meters, or the y value, is equal to 8 times the cosine of pi over 6h, time in hours, plus 12. We have some questions about this graph. At what time is the depth at 20 meters during the third cycle? So you can see the depth of the births at 20 meters repeats every 12 units, every 12 hours. So at the third cycle, we have 1, 2 is at 24, another 12 would give us 36 hours. Okay. The last part here, determine the height after 33 hours. So you're just going to plug in 33 into the time, and then your output from your calculator will give you 12. The last example here, a large wheel with a radius 15 meters rotates once every 100 seconds. So think of like a Ferris wheel. The passengers will mount the big wheel on a platform which is 1 meter above the ground. So don't forget that the lowest that the person can go, or the chair of the Ferris wheel can go, is at 1 meter. And then think of, you go to Tinkertown, I guess that's the only real Ferris wheel that we know in Manitoba, or maybe the Red River X. You sit down on the Ferris wheel, you start in that chair. You're going to always return to the same height that you started at. So you'll start at the bottom, you'll load on, you'll ride the chair to the very top, and then it continues on its circle and you're at the bottom again. Top, bottom. So wheels are a really good example of sinusoidal graphs because, of course, you can only move on that one axis. So your position repeats itself indefinitely depending on the number of times you go around that wheel. So there's some information here. They give us the period. It's 100 seconds. We start at 1 meter above the ground, and it has a radius of 15. So the midline will be at 16. 1 plus 15, of course. Sorry, this graph is not to scale perfectly, but you get the idea. Now that we are able to approximate the graph, we can write an equation for cosine that represents the height m as a function of time s. We know that our amplitude or height or radius of our wheel is 15 from here to here or from here to here. Our period is 100 seconds. It takes 100 seconds for that Ferris wheel to go around. So we have 2 pi over the period will equal b. Our b is pi over 50. C is 50. You can see that it's shifted over to the right here. And d is positive 16, or where that midline is. Beyond this, you have some practice questions that you can finish up, and then you can move on to the homework.